Hi guys, sorry I can't be there today. I'm moving my son into college at Purdue, but you're in good hands with Mr. Mauger, so anything that you're not understanding, please just let Mr. Mauger know. I know he loves to talk chemistry and would gladly help you with anything you're not quite understanding. So today we're going to be finishing up chapter 2 with section 3. First we're going to look at the differences between accuracy and precision. You probably have heard of these before in other science classes, and like I said the other day, a lot of what we do, especially in the lab, is dealing with measurements. So anytime we're trying to make a measurement of something, whether it's a volume or a mass or something like that, we want to try and be both accurate and precise. Accuracy represents the closeness of a set of measurements to the correct or accepted value, which is what that first dartboard on the left is showing. All the darts are right on the bullseye being the accepted or correct value. And so the person throwing the darts was accurate with their dart throwing by hitting the bullseye each time. Precision, on the other hand, this one you may not be as aware of, but that represents the closeness of a set of measurements to each other, which is what that middle dartboard looks like. So even though they're not on the bullseye, all three of the darts are in relatively the same location. So that person was being precise with their throwing, but they weren't being accurate. Okay, and oftentimes precision is something that you can't necessarily help, especially like with the balance. Maybe the balance isn't properly adjusted, so all of your measurements might be slightly off. But what we don't want to see is that that dartboard all the way over on the right hand side, where you just have darts all over the place, where you're being neither accurate or precise. So again, the goal when we are making measurements, take your time, make sure you're trying to be as accurate and precise. And when we get to the next slide, we'll be talking about Sig Figs, and that's the other thing. Anytime you make a measurement, you always want to record all of the proper Sig Figs, and we'll talk about that more in just a little bit. So in labs where we are doing what we refer to as quantitative lab, I know we talked about qualitative and quantitative in the metric activity the other day. Quantitative lab is where we're using data from measurements, and oftentimes we're going to be ending up with an overall value for something that we were making or doing in the lab, and we can compare that to the true or accepted value, and that's then we can compare how accurate we actually were with that value, and that's what we refer to as percent error. So it represents the accuracy of the value you came up with, or the value you measured. That's the experimental value. That's the one that you are coming up with, and we compare that to the true accepted value. So like yesterday when you were doing the metric activity, you were all measuring the height of your desk. You know, there is one true acceptable value for the height of your desk, and you may have measured it to be exactly that. You may not have. So we can look at how accurate your value is by its percent error, and the way we calculate that is we take the accepted value, what the value really should be, minus your value, the experimental value. And if you notice, there's those vertical lines around those two things. That means we take the absolute value. So regardless of whether your experimental value is larger or smaller than the accepted value, we always make that a positive number, because we don't care where you too far above it or too far below. We just want to look at how far off of the accepted value you really are. So we always make that positive, and then divide that value by the accepted value, and to turn it into a percentage, then we multiply by 100%. So here's an example of how we would calculate a student's percent error. So if a student went to a swimming pool and used the meter stick to measure the depth of the pool to be 2.04 meters, but the actual accepted value is 2.00 meters, we can calculate the student's percent error, how far off of the accepted value they were. So we plug in the accepted value of 2.00 minus the student's value, the experimental value of 2.04, and again take the positive value, even though technically that would come out to be a negative 0.04. We do absolute value, and then divide by 2. Then to convert that will give you 0.02, and then to convert that to a percent, we just multiply it by 100. So the student was off by 20%. And again, that's not horrible, but again, our goal is to try and be as accurate as possible in our measurements. Okay, the next part of section 3 is probably the biggie: significant figures, or Sig Figs for short. The other day, some of you were asking, how far out should I keep numbers on my answers and stuff, and for the other day, told you not to worry about it. From here on out, though, when you're doing any math problems in chemistry, you need to think about Sig Figs and how many numbers you really should have in your answer, because even though the calculator may give you 4 or 5 numbers, you don't necessarily need to use all of those. It depends on how many Sig Figs your answer should have. So Sig Figs represent a measurement that is consisting of all of the digits that are actually measured plus an estimated digit. Oops, sorry. Let me go back. So as you can see over here on this picture of the door, there we go. There we go. Depending on the markings on the ruler, we can have more and more significant figures, and therefore a more and more accurate measurement of this door depending on which ruler we use. Here, this top ruler, or meter stick I should say, really doesn't have any markings at all. It's just 1 meter in length. So the best that we can do to measure that door is just estimate that somewhere between, I keep losing my cursor, sorry, there we go, is to estimate that door is somewhere towards, closer to 1 meter than less than that. So they've estimated it to be 0.8 meters. Okay, and that's the best we can do because there's no other markings to make that answer any more accurate. Now this next meter stick down here has every 10 centimeters marked on it. So now that we have a few more markings, we can actually be a little more accurate and have more Sig Figs in our measurement. And so here you can see that it's not quite up to 80 centimeters, which would be 0.8 meters. It's actually a little bit less than that. So we can estimate, we know it's more than 70 centimeters or 0.7 meters, but it's not quite 0.8 meters. So we can say that the value of the length of this door is 0.7. That's our actual measured number. We know that based on the 70 and the 80 here, and then we can estimate the other. In this case, the book estimated that it was 7, but you might say, I think that's more like a 5 or a 9. The estimated digit can vary. Usually we just use 0s or 5s, but here they used a 7. So this first 7 is what we can actually measure from the ruler itself, and then the second one is estimation, which it can vary from one person to the other. So now with this ruler, we can have 2 Sig Figs in our measurement of the door. And then down here below, this bottom ruler has even more markings. It actually has these little hash marks. Those are the millimeters. And so now we can be even more accurate and have an additional sig fig, and we can see now here it's still between the 0.7 and 0.8, or 70 and 80 centimeters, but now we can count the little hash marks over, and it is just past the 7 millimeters. So it is 0.7 from this 70, and then 7, and then we can see it's kind of in between the little hash mark that represents the 7 and the hash mark that represents the 8. So that's where they're estimating that additional sig fig as being a 2. Again, usually when we get to the estimated number, we would say a 0 or a 5. 0 meaning it's right on the 7, or a 5 meaning it's kind of halfway between the 7 and 8. But that 7 here now represents the 7th hash mark up here, because this has these extra markings, and then the 2 is our estimated digit. So this value has 3 sig figs, where this first one only had 1, the second one had 2, the third one had 3. And that one's the most accurate measurement because it has the most sig figs. So first, before we worry about doing any math, let's look at rules for how we can determine how many sig figs a number has. Now, when we're in the lab and we're making measurements, like with your rulers the other day you were using, the directions said you could carry it out to the 1/100ths of a centimeter. When you're making measurements with different instruments like the rulers or the graduated cylinders, that's where you yourself need to look at the markings and the hash marks so that you can include the correct number of sig figs. On your homework and stuff, you're just going to need to be able to look at the number and count how many sig figs that number has based on these rules. So the first rule is any non-zero numbers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, those are always considered significant. So like in the number 78, that has 2 sig figs because both 7 and 8 are non-zero numbers. So whatever it was that we were measuring, we measured it to be 78, whatever, 78 grams, 78 meters, liters, whatever, that number has 2 sig figs. Now the tricky part, and the rest of these rules are all based on zeros. Zeros is where sometimes zeros are significant, sometimes they are not. If we have what we call a final zero, or zeros that are to the right of the decimal, okay, so if there's a decimal place in a number and there's a 0 on the right side of that decimal at the end, it's got to be a final 0 at the end of the number, then that 0 is significant. So like here, instead of just plain old 78, if we have 78.0, that 0 is at the end of the number on the right side of the decimal, so that 0 is significant. So this number has 3 sig figs. And just like this ruler, that must mean whatever we were measuring this value to be, we just have an instrument that has more markings, so we could include that 0. Or likewise with this one, 0.780 right here, so that is a 0 at the end of the number to the right of the decimal. That is also significant. So both of these numbers have 3 sig figs. Now this 0 in front of the decimal, I don't know what its actual title is. Mr. Mauger might be able to tell you. I always call that like a courtesy 0. That's just to help you see that there's a decimal point there. So that 0 is never significant. So when we have a number less than 1, the 0 out in front of the decimal point is not counted as a sig fig, and because it doesn't even have to be there. You could take this 0 away and it's still going to be the same value without it. Okay, the next rule is when we have zeros between sig figs. So anytime we have a 0 between two sig figs, that 0 is also significant, because whatever it was we were measuring to get that number was allowing us to have that 0 in between those two sig figs. So like the number 708, that is significant. So there are 3 sig figs with that number. The tricky one that people have the most trouble with are when zeros are just placeholders. Okay, and that's where we need zeros to put the numbers that we actually did measure that are significant in their proper place value, but we didn't have the ability to measure the place value of those zeros. So like the number 780, if there's no decimal at the end of this number, then that 0 is not significant. So 780 without a decimal point only has 2 sig figs, the 7 and the 8. This 0 is just there so that the 7 can be in the hundreds place value and the 8 can be in the tens place value, but we could not, for whatever reason, measure a number in the ones place value. Likewise, again, we already talked about this first 0 not being significant, but these other 2 zeros here, even though they're to the right of the decimal, they're not at the end of the number. So because they come in front of the number, those are just placeholders as well, so that the 7 can go in the, what would that be, the 1,000ths place value, and the 8 can go in the 10,000ths place value. So both of these numbers just have 2 sig figs. And then counted numbers, like to count all of you guys up in class, those and constants that we'll get into and use all throughout chemistry, those have infinite or unlimited sig figs. So we never use counted numbers or numbers that have been converted into constants towards sig figs, okay, because those are considered unlimited or infinite amount of sig figs. Okay, so let's try these. Oh yes, and scientific notation, when we are writing a number in scientific notation, we only include what is significant. So like up here, this 78.0, since that 0 is significant, if we were to put that in scientific notation, that would be 7.80 times 10 to the 1 power, because that 0 is significant. But down here, 780, since there's no decimal point at the end of this number and that 0 is not significant, 780 would just be 7.8 times 10 to the 2nd power if we were to put that in scientific notation. So we would not include that 0 here. So here, if we take a minute and count up how many sig figs each of these numbers have. So we have 0.05730, 40.0007, 6,020, and then 3.10 times 10 to the 4th. Okay, so let's take a look at these. So for 0.05730, hopefully you said it was 3. I'm sorry, 4. My bad, I can't count. So this 0, again, this first 0 is just a courtesy 0. This 0 is just a spacer so that all these other numbers that are significant are in the right place value. And this 0 here, because it is a 0 to the right of the decimal at the end of the number, is significant. So the 5, 7, 3, and this 0 are the 4 sig figs. The 40.0007, all of those zeros are significant because they're crammed in between a 4 and a 7. So even however many zeros there are, if they're in between two sig figs, they're always significant. So that's why that number has 6. Now here's 6,020. This 0 here in the middle between two sig figs is significant, but this 0 on the end, because there's no decimal, that is not significant. So to make that 0 significant, we would need a decimal point right here. So this number just has 3 sig figs, the 6, this first 0, and the 2. And this 0 is here just to put those 3 values in their correct placeholders. And then finally this one, 3.10 times 10 to the 4th power, that has 3 sig figs, because if this 0 was not significant, we would not put that in scientific notation. So if it only had 2 sig figs, it would just be 3.1 times 10 to the 4th. Okay, and that does follow the rule of ending zeros to the right of the decimal. So when we put it in scientific notation, a 0 at the end of the number on the right side of the decimal is significant. So that has 3 sig figs as well. Okay, now what we'll be doing all throughout the year is doing math with numbers that have sig figs. Now we won't be doing a lot of addition and subtraction, although, you know, on the first slide we were doing percent error, and in that case we would want to follow our addition and subtraction rule for that, but there's only a couple different times that we use addition and subtraction. The main one that we use all the time is multiplication and division. But first let's look at addition and subtraction. So for addition and subtraction, the answer can only go to the least place value. So whatever number has the least place value, that's what we use to decide how far out to carry our answer to. So here with the number 25 plus 3.2, now if you plug that into your calculator is going to give you 28.2. But because the number 25 only goes to the ones place value, over here the 3.2 goes to the tenths, but we don't, whatever this was that we were measuring, we couldn't go to the tenths place value with the number 25. So that means our answer has to stop in the ones place value as well. Okay, so since 25 stops at the ones place value, our answer has to stop at the ones place value. And it's the same for subtraction as well. And again, multiplication and division is the main type of math operations we'll be doing. And in that case, this is where knowing how many sig figs you have in a number is very important. So the answer can only have the least number of sig figs as any of the numbers you plug into the problem. And that's because your answers can't be more accurate than the numbers that you were able to measure. So if we take, and I know this is going to blow your minds away because math doesn't really worry about sig figs, but if we multiplied 80.0, which has 3 sig figs, all of those zeros are significant, times 2, obviously you plug that in your calculator, that's going to give you 160, but that is not right in the world of sig figs. So even though 80 has 3 sig figs, the number 2 only has 1 sig fig. So that means our answer can only have 1 sig fig, which, as long as we don't throw a decimal point in here, 200, because we would round up, we'll talk about that more in just a second, we would round 160, ouch, just hit my knee, we would round 160 up to 200 to make it just 1 sig fig. Okay, so I know that's really hard for a lot of people, but again, you can't just copy down the numbers from your calculator. You've got to sit and think about, okay, how many sig figs should this answer have, and then do I need to round it or not? So rounding, when we decide, do we need to round up like we did here from 160 to 200, we look at the digit next to the last sig fig. Okay, so like with the 160, the 6 is the last sig fig. Well, it's not the last sig fig. The 6 is the last digit next to the sig fig that we can only have one sig fig. And because it was greater than or equal to 5, we rounded up, which is how we came to 200, as opposed to if 80 times 2 was 140, instead of 160, we would round down to 100. So if it's less than 5, we don't do any rounding. We would leave it. Okay, so like I said, we up here with the 160, because the 6 can't be a sig fig, we can only have one sig fig, and it's greater than 5, that's why we rounded up to 200. If it were 70.0 times 2, that would obviously equal 140. With only one sig fig, we would round down to 100. And when we have multi-step problems, like in factor labeling or something else, keep an extra sig fig until the very last step of your final answer, and then look at how many sig figs, the numbers you were using. And again, don't use constants and things like that, but always keep an extra sig fig until the end, and then go ahead and figure out how many sig figs your final answer should have. Okay, so try these here, this first one. And sometimes with addition and subtraction, if you line them up vertically, that might make things a little easier to see what place value you want to carry your numbers to. So I'll give you a few seconds to do both of those. Okay, so again, with this first one, we're adding. And so again, addition goes by place value. So since both the 61.2 and the 8.6 stop in the tenths place value, our answer can only go to the tenths. Even though this one goes to the 100ths, our answer can only go to the tenths. So your calculator, when you plug that in, will give you 79.15. But again, we have to stop at the tenths because of these two numbers. And since this is a 5, we got to get rid of that 5, and it's a 5 or greater, we would round that 1 up to a 2. So the correct answer would be 79.2. Over here, 8.3 times 2.22. Now the 2.22 has 3 sig figs, but 8.3 only has 2. So when we're multiplying and dividing, again, we go by the least number of sig figs. So since 8.3 only has 2 sig figs, we cannot keep all of these numbers in our answer. We cannot make this 18.426 like your calculator says. We have to round it to just 2 sig figs. And since 4 is less than 5, we don't need to round up. We can leave it at 18. So the answer would actually be 18. Okay, so again, if you have any questions, Mr. Mauger will be happy to help you. But once you finish up your notes, go ahead and get the homework sheet from Mr. Mauger. And again, he's willing to help you with your homework as well. And we'll also go over a couple answers before I collect it in our next class period. So have a good day, and I will see you next week.